All right, so now we are going to start the most important part of this class. We're going to talk about CUDA, okay? Because this probably new for most of you, and I think half of you probably try to enroll this class because you do want to know how to do programming on GPU, right? And the programming language we're going to introduce is CUDA, okay? All right. So there are many things we need to teach about CUDA so you can do GPU programming. And so we have couple of lectures on this topic. And for the first lecture for this slides, we're going to just give you a brief introduction about CUDA. So after this, I think you already have a concept, or at least basically you should have the ability to do some simple GPU programming already. Okay. However, if you do want to improve your performance and optimize your code, then you also need to know the detail of the GPU architecture. Because as we mentioned, the programming model usually is just an abstraction of the hardware. So if you know the GPU architecture, then that should help you to understand how to do the programming, okay, or how to diagnose the problem, or analyze the performance, or optimize your code. So we will introduce the GPU architecture in the next lecture, and then we have another lecture specifically for optimization. So we will teach you some techniques, advanced programming to optimize your code on GPU. And actually a lot more to learn for GPU programming, because GPU is rapidly advanced over the last few years, and we can expect the same trend for the future. So it's not just the performance is even better. Actually, it provides even more functionalities and optimization, maybe optimization API or techniques. So if you Google online, you can find there are a lot more API or optimization techniques that could be used on GPU. But of course, for this course, we have limited time, so we will only cover the basic. So at least you have an idea about the CUDA and the GPU programming. And when you look at a CUDA code, right, or any GPU code, hopefully you have enough knowledge to understand it and know where to look for the further information on yourself online. Okay. All right. And of course, we have homework for this, and that will be your homework 3. Okay. All right. So for the basic, right, just for the CUDA programming from the software point of view, we will briefly talk about the programming model of CUDA, and then talk about the API, some of the specifier, and some of the basic definition, or right programming method for CUDA. Okay, and then we will use a few simple application as an example to make sure everyone knows how CUDA programming works. Okay? And then we will talk about, you can see the relation between GPU and CPU, right? So we are doing heterogeneous computing, not just GPU computing. So you need to be clear about the the relation, at least the synchronization between CPU and GPU. So you can know exactly, you can expect how your code will run across both CPU and GPU. And finally, of course, if you want to utilize more GPU power, then the easiest thing is to utilize multiple GPU, right, on a single server. And that's exactly what you will do for your homework as well. So we will talk about some of the basic, or the principle of data management across multi-GPU. Okay? All right, so a lot to cover. So first of all, right, what is CUDA? Okay, so it's a abbreviation for Compute Unified Device Architecture. Okay, so you can see unified device, right? So it's actually for across GPU or across CPU and GPU. So it's for heterogeneous computing basically. Okay, and the CUDA itself, like we mentioned, right, include the compiler, the toolkits, include lots of things, all the things you need to do programming on a media GPU. Okay? And as we mentioned, right, it's enable heterogeneous computing and allow you to access the massive computing power from GPU. And this API is an extension for C and C++. Okay. Today, I think it also have the extension for other language, but for this course, we will, of course, only talk about extension from or C and C++. Okay. And it's a programming abstraction. And of course, this abstraction is, you can say, is abstraction of a SIMD processor, because GPU in general can be think as a SIMD processor. But as you will find out, it's actually a lot more complicated than that. Okay. And we mentioned before, right? Just mentioned that depends on what's the CUDA version and the architecture. You need to make sure they can support the same compute capability. So they have intersection between the hardware and the software, so they can so they can work together. Okay. All right. So before we jump into any code, so you need to know how the CUDA program, right, is run on GPU or run across CPU and GPU. And as we mentioned, the GPU usually referred as the device, and the CPU usually referred as the host. Okay, and they are connected by usually the PCIe bus, right? And for the host and the device, they both have their own memory and their computing unit. Okay. So if you want to run a CUDA program, because it's a heterogeneous computing program, so at the beginning, of course, you are running on the host. Okay. But when you try to run something on GPU, then you first have to copy the data from the CPU memory, the main memory, right, to the GPU memory, which is the device memory or the global memory on GPU. Okay. And after you prepare the data, then you have to make a code, to make a function code that will be launched on the GPU. As you will see, the unit we offload to GPU is by function. Okay, so this function specifically, we usually code it as the kernel function. Okay, so what you will learn is to write the kernel function. Okay, and so after you write it, right, you have before you can run, you have to launch it on GPU. Okay, and once the kernel function is launched on GPU, it starts to execute it by accessing the memory, right, you prepare on the device memory. Okay? And of course, the result will also only be written to the GPU memory, on the GPU memory. So if you want to display or access by the host, you have to copy the data back to the main memory, right? Otherwise, your code running on CPU cannot access the GPU memory. Okay, so those four are the basic steps or the flow, right? You have to follow in order to complete, in order to run a GPU program on GPU. Okay. However, of course, this is actually not always the case, because there are a lot of optimization functionality and techniques provided by GPU or the CUDA library today. So later on, you will see there are other way to do this, handle those memory. So probably you can avoid step 1 or step 4, etc. Okay, but for now, we start from the basic, and the best way to understand how the code is working on GPU is the remember this picture. Okay. All right. So the CUDA program, as we mentioned, right, it's a heterogeneous computing program. So your code consists of the code for CPU, which runs on host, and we assume it runs on, or we can say no, it's the serial code, right? Because supposed to run on a single core. And there are codes that's for GPU, and obviously GPU has many cores, so you are using the threads to parallelize your code to do the parallel computation, okay? And running on the GPU device. Okay, so you can say your code, right? Any CUDA code is consists of serial code and the parallel kernel, because we said the function is called the kernel. Okay, and so you have two types of code actually in your program. Okay, and they will be executed either on a host or on device. Okay, okay. As we mentioned, right? So those code, how can we switch between the two, right? And how we realize the four basic steps we mentioned. Okay, so this is the pseudo code, right? For basically for all the CUDA code, you will see they are written pretty much the same as what we show over here. So remember, first step is to copy the data from main memory to GPU, right? So you have to code the CUDA main copy, do that. And the GPU memory is completely managed by the programmer. Okay, the hardware does nothing. Okay, he doesn't do it. He doesn't know do any. Doesn't know how to do anything. So it's totally controlled by the programmer through the API. Okay, so if you see a CUDA in front, that means it's an API code by the host. Try to manage the GPU. Okay, and for the GPU memory, right, you have to allocate it first before you use it. So you will need to code the CUDA main copy or malloc, and then code the CUDA main copy to move the data, okay, to prepare the data. And then the step two, remember, is to basically offload the kernel function or launch the kernel function. So how to do that? You can see it's in the form of a function. So just like regular function code, but you have this, right? You have this bracket in between. So to indicate it's a no, it's a kernel code. It needs to be run on GPU. And the unblock and the block size are the two arguments or the parameters that decide how many threads needs to be used to run this kernel. And we will talk about in detail later on, but basically you can see that those threads are grouped in they are grouped in blocks. Okay, so that's why the number of block multiply the block size equal to the total threads you're going to use for executing this kernel function. Okay, and when we declare this kernel function, you can see in order to that the compiler knows that this function needs to be compiled into GPU instruction. So we have this underscore underscore global underscore underscore. Okay, so this specifier to indicate this function needs to be compiled into GPU instruction, and this function will be launched by the host, okay, or to be called from the host to launch this kernel. Okay? And of course, after you make this code, then you will you will start execute the GPU code. That's our step 3. And step 4 is to copy the data, right, from device memory back to the host memory. So that's why usually you have a CUDA main copy after the kernel function, and then start the CPU code before this GPU code or after this GPU code. Okay? All right. So the basic CUDA code always looks like this. Okay. Now we have a closer look at the kernel. Okay. So as we mentioned, right, kernel is executed by many threads concurrently. Okay. So the code will looks like this, right? This is what we We mentioned this is basically a single program, multiple data programming model, right? Very similar to what the code you wrote for MPI, right? So I think right now you have enough knowledge and experience to understand this code already. So you can see instead of the rank ID for MPI, here we have thread ID for GPU. Okay, so again, this thread ID is predefined and pre-decided. So in your code, you can just directly use this in your code. And the result is every thread, right? It can execute the same code, but applied it on different data. So this is a no, this follows the single instruction multiple data um, no, model, right? Okay. Actually it's not that hard, right? So you can see just write a function and usually and probably you can only be applied you can only be used for data period, applied it on some array. So you manipulate those array index in order to parallelize the computation across some set of data. Okay. Okay, all right, and then so you can imagine a single kernel, is executed by even thousands of threads at the same time. So there are many threads. Okay, and the threads on GPU is actually a little bit different from the thread from CPU in terms of how those threads are executed and interact on the hardware because as you should know from your operating system course, right, that if a thread that needs to be context switch, you actually need to store or load the register to memory, right, in order to do the context switch, which is quite slow, okay, because you have to access the memory in order to do context switch. But on GPU, context switch will happen a lot more frequently because if you remember, we said that the number of GPU core, right, usually is much fewer than the number of threads you can concurrently run on a GPU. And the reason is because those threads usually will share the same core during execution. Okay, so that means they will context switch very frequently. And the reason for that is that the reason you design to have you have more threads than the core is because the memory store problem. The memory store problem. Okay, the memory store problem means that the memory access time usually require maybe 10 or 20 instruction cycle, but the instruction only takes maybe 2 or 3 cycles. So memory access usually is much more slower than the instruction. Okay, so whenever instruction try to access memory, we will try to context switch or suspend that thread and context switch to another active threads that's ready to run. Okay, so if you have more threads, then of course, right, you can wait for longer memory access time, and you can have more threads ready to utilize your computing power. So that's why the hardware design is to have more threads than the core. And as a result, you have to context switch frequently among those threads on GPU. So in order to make sure the context switch time is very fast and almost spend no time, usually the solution on GPU is to prepare individual register set for each thread. Okay, so that's why the thread on GPU is also called the physical thread because it physically exists in the hardware. Okay, they actually don't share the register to each other. Okay, so that ensure you can context switch very fast, very frequently among those threads, and to ensure we can hide the memory store problem. Okay. All right, so it's just good to know so you can understand why no why the design of the GPU is like that. Okay, right? For those threads, right, you can have maybe up to no even more than thousands of threads, right? How those threads are managed actually is, as we mentioned, those threads are managed by group. Okay, each group is what we call the block. Okay, so the threads to run the kernel function usually consists of thread blocks, and each block, of course, contain of multiple or even thousands of threads alone. Okay, so this is a hierarchical representation of the threads, right? And as you can imagine, this also match to the architecture of the GPU hardware. Because remember, each thread is corresponding to a GPU core, while the thread block will be corresponding to the stream processor. Okay, so each thread will actually be scheduled to a stream processor and use the cores on that stream processor to execute the threads you define within the thread block. Okay. All right. So the number of threads per block is actually bounded, right, by the number of core of a stream processor. So if you want to utilize more threads or you want to utilize all the stream processor, then you have to you know specify your threads by multiple blocks. So that's the only way you can run your code across the stream processors. Okay? Right? And as we will explain later on, although we say the GPU is a CD processor, it's like a CD processor. So supposedly, all the threads should execute the same instruction at the same time, right? However, it's actually not true, not entirely true, okay? Because we have a hierarchical hardware architecture. And the CD processor is at a very lower level, right? It's within a stream processor, and stream processor is within the GPU. Okay, so only the threads that executed on the same CD processor has that has to follow that constraint that the threads has to execute the same instruction at the same time. However, a thread block is running across the CD processors on a single string processor. So the threads within the block, if they are scheduled to different CD processor, then there's no guarantee they are synchronized, or there's no guarantee they are executed same instruction at the same time. So imagine, right, as we mentioned, for GPU programming, usually we are running or we are usually writing, we are usually doing the synchronous computation. So it's very common that we do need the synchronization, or we have a synchronization point across the threads. So in order to create that synchronization among threads, actually we have to use this API called the Think Threads. Okay, so this Think Threads API will force the threads to be synchronized. Similar is actually it's basically the same as the barrier code we introduced before. Okay. However, okay, this barrier will only be applied within a block. Okay, it cannot be applied across the blocks. Okay, and the reason is because this API is only supported by a stream processor within the stream processor. So if the threads are from different blocks, then those blocks may be scheduled to different stream processor. So that means the Think Threads API will only apply locally within each block. Across block, it has no effect. Okay? They only synchronize within the block itself. Okay? So you might ask, so what happens if you want to have a global barrier across thread block? It's not trivial because there's no API for it. You have to use some programming technique to achieve that. And that's one of the optimization technique we're going to talk about in the last lecture of this part. Okay. Okay. So you have to wait for a second. Okay. All right. We already talked about, right, several terms from the software and the hardware. So now let's put them together, how they are mapped to each other, right? How we abstract the hardware to the software in CUDA. Okay. So first of all, this is the mapping for from the processing point of view, right? From the execution point of view. So all we care for the hardware is, as we mentioned, at the finest level is the core, right? A single core. And the core is within the stream processor. Okay, that's the second layer. And a cross layer, right? A GPU card actually consists of many stream processor. So at the highest level is our GPU card. So the GPU also is also called the device we mentioned, right? Now that's mapped to the software. I actually already mentioned it, right? Partially, right? At the lowest level, we can manage its thread. And each thread, of course, needs to be executed or scheduled on some core, right? In order to execute the instruction. So the thread maps to the core. Okay. However, this mapping is it is one-to-one, but it's not a static mapping. That means a thread doesn't need to always run on the same core, okay, across the lifetime. Because you may encounter memory store, as we mentioned, then the thread will be context switch, right? Will be swap. So when it swap back and context switch back, it may just run on any core. Okay? However, no matter which core you use, it must fall into the same stream processor, because a stream processor mapped to the block, the thread block we mentioned. Okay, and the relation is again so one-to-one in terms of a single block, a single thread block can only be scheduled to one of the SM. And after it's scheduled to a SM, it will be bound on the SM. It cannot be migrated to other SM. No, no, afterwards, because in the SM on the SM we can see there is a shared memory, right? So some of the memory content will be created and placed on the string on the shared memory. So if you migrate the block across SM, that means you have to move those data as well. And that is too time consuming. It's not scalable, basically. So that's why once a block is scheduled to some SM, then it will stay there. Okay. However, the threads can run on any core within that SM, as long as there's a available cores. Okay. All right. So that's the thread block. And that's why we said that for single kernel, different blocks of threads can run on different SM. And the synchronization API only apply within the SM. It cannot be applied across the whole GPU. Okay. And finally, is the grid. Okay. Grid is another term we commonly use in CUDA programming. The grid, as we all know, right, referring to this, right, you have X and Y dimension. It's this is why we call the grid. And we use the term grid because we know for a kernel, right, it consists of many threads, and those threads are grouped into block. So this looks like a grid, right? So the grid basically usually is used to describe the dimension of a kernel, the dimension of the threads that run the kernel. Okay, so the grid usually is described by how many blocks and how many threads per block. Exactly the argument we need to launch a kernel, right? So that information is the grid size. Okay. All right. So so grid essentially is, you can refer into the kernel as well, but kernel usually is used to describe the code, the function, and the grid is try to describe the thread dimension or the size of the threads to run that kernel function. Okay. All right. So after knowing this mapping, um, we can understand why there cannot be any, or the GPU doesn't provide a global synchronization. The reason is that we want to make sure the SM processor, they can work and run independently to each other. That's why we can have a more scalable hardware architecture, right? And make sure the GPU can run more efficiently. Okay. Because the SM is completely independent, so we need to make sure, right, the code between the blocks are also independent. So that's why even for synchronization, we do not provide the synchronization across block. If you do that, you basically have to do the synchronization across string processor, and that's very costly. Okay. And to make sure the string processor and the block can be independent to each other, will help you to be more scalable, because as you can see over here, those thread block can be scheduled completely independently to each other on the hardware. So for example, if you have say a GPU with only two SM processor, then you have 8 blocks to run. Then those 8 blocks will be scheduled on those stream processor independently. And of course, let's assume each block can utilize all the core in a SM. Then you can only run one block on the SM at the time. Okay. So as a result, if you have 8 blocks, you have to run them 2 by 2, right? Two at a time, and takes 4 iterations to complete it. So that's why you can see. That's why we said no. The instruction or the execution across blocks or even across threads may not be synchronized in nature, because sometimes they even have to be executed in a serialized way. Okay. All right, and if you have a 4SM GPU, then you can see that the schedule can quickly, very efficiently utilize all the SM by schedule 4 or run 4 blocks at the same time and complete it in a shorter time, right? So you can see the GPU schedule itself is a block level scheduling. As we can see over here, that the programmer actually can decide, right, how many threads blocks you use and how many threads within the block is used to run your kernel. So you can decide the shape of the grid for your kernel function. Okay. And it's up to the hardware scheduler to do the mapping between the thread block and the stream processor. So although we have so many stream processor and the cores on a GPU device, but still resources are limited, right? So as we also mentioned, you can use like device query, right, to get some of the hardware limitation of your some of the limitation of your hardware, right? So you will see some of those information list over here, right, to indicate when you launch your kernel, what's the maximum size, right, you can use for a thread block or for a grid. Okay. And so this is the reason, right, you might need to use this command to figure out what's the limit you can use in your program. Okay. And some of the configuration, like we mentioned, like the maximum number of grid per device, right? That means because we said a grid is equal to a kernel function, right? So the maximum number of grids per device, that means how many kernels can be executed at the same time on this device. Okay. And the reason you might have multiple kernels running on this device, because the GPU may not just be accessed by a single process, right? So you can create many processes, and each of them can launch a kernel on this GPU. Then you have, right, multiple grids or multiple kernels running on the device. But at this, the maximum kernels can be run concurrently on the device is only 32, for example. Okay, or the number of threads per multiprocessor, which means the SM, right, string processor. This indicates, right, how many threads can be actively running on a string processor. The threads can come from different blocks or even from the blocks of different kernels. It doesn't really matter. This limit is set for the SM from the SM point of view. So no matter how many kernels or blocks are scheduled to this SM, at most, it can only run up to 2048 threads at the same time concurrently on that SM processor. So you can see there's always a limit for your execution. And the result of this limitation is that some of the blocks, right, will be queued and waiting in the device queue, right, until the SM is available. Then the block will be scheduled to the SM. Okay? Right, and also the maximum number of threads per block. This is same as before, right? This is the limitation of the block size you can give it in when you launch the kernel. Okay, so you need to know those limits because usually you do want to maximize the hardware resources usage, right? At the same time, you cannot over those limits because your code will cannot be run if it's over those limits. Okay. All right. So we talked about the mapping for processing, right? Here is the mapping between the hardware and the software for your memory or variable. Okay. So you can see on the outside is the global memory, and the global memory usually maps to the kernel. Okay. And different from other memory, the global memory, the lifetime of a global memory is equal to your the lifetime of your process. Okay, so remember you need to use the API to allocate the memory and move the data between the global memory or the device memory and the host memory on your own. So actually, if you don't try to free the memory, then the memory will be always there. So it can be persistent and keep alive across kernels. So it's actually a way for you to pass the variable or the info or the memory content across kernels. Okay, because its lifetime is the same as your process. Okay, you will only be free if the user, the programmer, code the CUDA free, or if your process is killed or terminated. Okay. On the other hand, for the shared memory and the local memory of the register, their lifetime is only be the same as the lifetime or the execution time of a single thread block. Okay, so the lifetime, this one, after you finish your kernel, then those memory space will be free for sure. Okay, and the local memory of the register, of course, maps to the local variable, right, defined within the thread, and the shared memory. The shared memory, it is it's declared and it will be used by your code within the kernel function, and we will show you those later on. Okay, so different from the local memory, the shared memory means the memory content can be accessed by all the threads within this block. That's why it is called the shared memory. Very much like the global memory, right, across CPU threads in the multi-thread program. Okay. However, this block, right, a single CUDA function actually is consists of multiple block. Okay, so those shared memory can only be accessed within a single block, right? And as we mentioned earlier, you know that the global memory is actually a memory chip outside the string processor. So its size is larger, but it's also slower. The access memory time is slower because it's far away from the core. On the other hand, the local memory and the register and the shared memory, they are both on the string processor. So usually they are also called the on-chip memory, while the global memory is called the off-chip memory. And the on-chip memory definitely will be faster than the off-chip memory, right? And the memory space of shared memory is larger than the local or the register because shared memory is shared by all the threads, while the register can only be used by a thread only. So that's why the registers available to a thread is less, right, fewer than the size of the shared memory. Okay, all right. So how to manage your data, right, on those on this memory hierarchy is the key for GPU programming. And each memory will be managed by different way. Like global memory is manipulated by the API, and the shared memory is manipulated by the memory declaration and the memory assignment. Same thing for the local register. Okay, so they are managed by in different way. So that's those are the API we will talk about next. Okay. All right. And same thing for memory. Of course, there are limit, and as we mentioned, right, the number of registers is definitely smaller than the size of the shared memory, which is smaller than the size of the global memory. And for GPU, there are a couple of more memory that's they are special designed for GPU rendering, but they can also be used for general purpose programming. So one of the memory is called the constant memory. The constant memory is actually also off-chip memory. So it is very pretty much the same as global memory, located at the same place. However, we all know constant means it's a read-only. So if it's a read-only, that means the memory content read out from the constant memory can be cached to the string processor. Because it's a read only, so we don't need to worry about the synchronization problem. So manage the cache data is potentially free. However, for global memory, because it can be written, can be modified, so if you cached it on the string processor or cache in other places, you have to resolve the data consistency issue, right, or data coherency issue. So in the past, it's not even allowed to be cached at any place at all. But today, the latest model, they do provide cache for global memory, but still, you might pay a higher price for that. Okay, so that's why usually we do use constant memory as optimization for storing the read-only data. Okay. All right. So those are the terminology we have introduced, and um, you need to remember it, right? In order to understand or to imagine, you could imagine how your code will be run on the GPU. Okay. All right. So here we have a couple of quiz, right? So if you are able to answer those questions, then I'm pretty sure you have a clear concept about how the hardware is abstract in CUDA. Okay. And on the other hand, if you cannot answer the question, then you need to make sure you understand it as soon as possible. Okay. So the first one is, can the kernel run across multiple SM processors? Anyone want to give us an answer? Yes or no? Anyone want to volunteer to answer this? Okay, the answer is should be yes, right? As long as the kernel has multiple blocks, then it is possible to run across multiple SM. However, whether those blocks are scheduled to the same SM or different SM uh, is depending on the hardware scheduler on GPU, inside GPU. It's not controlled by the programmer or the CUDA code. Okay. Secondly, does the kernel below have to run on 10 different SM processor? Obvious not. Okay. So, by the way, the first 10 means you have 10 blocks, and the second 10 means each block has 10 threads. We only care about the first one here because 10 blocks potentially it could be run on 10 different processor, but not necessary. Okay. Third question, can the threads from the same block run across multiple SM? No, of course not, right? So a block is a unit when we dispatch the threads to SM processor. Okay, so a block cannot be separated or divided across SM. Okay. What's the difference between the two kernel launch below? Okay. First of all, they do have they do have the same number of threads at the end because the first one says it will be run on a single block with 100 threads of that block, and the second configuration says I will run it with a 100 block and only one thread per block. So in total, they both run the kernel with 100 threads, but they're using different number of blocks. And how will that be different in terms of the performance and coding? In terms of the performance, it depends. Okay, if it's only one block and 100 threads, it could be run faster if because it's run on the same block, so you can explore some data access pattern to optimize the performance, as we will teach you later on. Okay, in order to take advantage of those hardware acceleration or memory access optimization, the first thing you need to make sure is those threads access the data in a continuous way from the same block. So that's why usually and most likely, if you use one block with multiple threads, you can get a better memory access performance. Okay? However, it could produce a worse performance if the GPU is highly loaded, and it's difficult to find any SM has more than 100 core available. So in that case, you might be blocked and wait until you have that space from a single SM. And also, because you only have one block, that means you cannot fully utilize the GPU at all, right? It's impossible because this kernel can only run on a single SM. So it has a lower degree of parallelism. Okay? On the other hand, if you have 100 block and only one threads, it gives you the highest parallelism because every thread can be scheduled independently. However, because they remember the collective I/O we introduced for MPI, right? So it's the same thing. Okay, so if you are within a block, you can use collective I/O to accelerate the I/O speed. But if they are separate into blocks across SM, then you cannot perform collective I/O. So the I/O time, the memory access time, maybe becomes slower. Okay? So that's the drawback. Okay. Okay, the next question is a shared memory can only be accessed by the thread within the same block. Yes, of course, right? So that's the limitation and the data access scope of a shared memory. It needs to be within the same block. Okay? And next, why we have to call sync threads within the block if there are data dependency between statements. So basically, as we explained, a block, the threads of the block can be run on multiple SYNC processor within a SM processor. So you still need a sync threads to synchronize the threads within the block. Okay. However, this API cannot be applied across blocks because that means you need some hardware synchronization mechanism exist across the SM processor, and that's not what we want to do. So the GPU doesn't provide that synchronization mechanism. Okay? All right, so that concludes the first part, and hopefully now you have a good idea about the basic terminology and the entity, right, in CUDA programming. And next, we will talk about the API for CUDA programming. And in fact, for basic programming, again, there's not that many things you need to remember. What's hard for GPU programming is to resolve data dependency, right? And also optimization is very, very challenging if you want to reach the best performance, because there are too many skills and there's too many tricks from the hardware. And we will talk about that in the optimization lecture, okay? All right. So what you need to know for CUDA programming, basically we already saw half of it, right, in the previous example. So the first one is the kernel launch command, right? So it's just a function code, but you will use the bracket to indicate a couple of arguments. And we already explained the first two arguments, the number of block and the number of threads per block, which describe the grid size and the block size. Okay, and there are actually two more arguments you can give when you launch the kernel. The third one, however, those two are optional because they are for optimization. Okay? The third one is a shared memory size. Okay, so as we all know, what's the shared memory? So to allocate the shared memory, there are two ways to do that. One is to allocate it, during the compilation time, and the other is to decide the memory size at the runtime with this argument. Okay, although it's a runtime, but you can see you still have to specify the exact size when you launch the kernel. So still the size is already decided before the kernel is executed on the GPU. It's after the code is executed by the host, but still needs to be decided before the kernel function executed on the GPU. Because GPU is actually quite dumb, or the GPU allocation mostly managed by hardware. So at runtime, dynamically, it doesn't want to support operation that's too complicated. Okay, so the memory size still has to be predetermined before it runs on GPU. Okay, and we will introduce those two ways of memory allocation on shared memory later on. Okay, the fourth argument is a string ID. And again, string is the optimization technique provided by the later version of GPU and CUDA. And basically, we'll introduce later as well, but just briefly talking about it. The string ID is used to implement your code or run your code in a pipeline fashion. Okay, so a kernel, actually you can launch the kernel, you can launch multiple kernel at the same time and overlap their memory copy time with the execution time of another kernel. So in order to run concurrently, run two kernels at the same time on a GPU, you have to use the string. Okay, otherwise, a single process only map to a single string, and all the kernel function run on a string must be serialized on GPU. Okay, we will talk more about this later. Okay, so anyway, to break that limitation, to allow us to run our function code, our kernel code concurrently, like the pipeline strategy, we will need to use the string. Okay, if you don't specify this, then it's equal to telling the GPU that the kernel is launched to string 0. And so you can imagine all the kernel will be launched on the same string, on the default string. So as a result, as I said, those kernel will be executed in a serialized version on in the serialized manner on GPU. Okay. Okay, so next thing you need to know is the built-in device variable, right? Like the rank ID from MPI. So here we have the thread ID, the block ID, and the block dimension and the grid dimension. Okay, and the block dimension is exactly this argument. It's the same value. So it's just copied to this block dimension variable. And the number of block is the value that's copied to grid dimension. Okay? And the reason you need those two dimension information is because you might need to serialize the thread ID and block ID, right? You need to serialize them across, say, a one-dimension array, right? So because threads is described in two dimension, so if you want to linearize, I should say, linearize into one dimension to operate on a array, on a data array, then you will need those dimension information, right? All right. And the third is intrinsic function. There are a couple of intrinsic function, not just the sync threads we introduced, but here we use sync thread as example. So you might find other intrinsic functions. Okay, and the point you need to know is that intrinsic function here, always start with underscore, two underscore. Then this indicate that this function will only be called and applied in the kernel code. Okay, so not like the CUDA free, CUDA main copy. Those are called by the host threads, right? The host process. If it's an intrinsic function, that means it's applied on the GPU, and it can only be called within a kernel code. Okay? And finally, there are some specifier. Okay, you already saw one, right? Like the kernel function, you have to have this global specifier before it. So those specifier is for compiler. Okay, so the compiler will knows whether this function code will be compiled to the GPU instruction or the CPU instruction. And for the variable, it tells compiler whether this function will be allocated on the device memory or the shared memory or the register. Okay, so we will talk about each of them in more detail. Okay, so first of all is the thread ID and the block ID. Okay, we already saw the example of the one-dimension thread ID and block ID. They are just some integer value, right? But as we know, GPU originally is designed for image, and the image we often have those two-dimensional image or even three-dimensional image, right? And it just happened that for the general purpose computing, we also often apply GPU on matrix operation, right? And we have those two-dimensional matrix or even three-dimensional matrix. So the data type of the thread ID and block ID actually can be up to 3 dimension. Okay, so if you want to declare a three-dimensional thread ID or block ID, what you need to do is to declare the variable as a dimension 3 data type, and you can have x, y, z to indicate, right, the length of each dimension. Okay, so let's look at the example first. It's easier to understand that. So for the grid size and the block size, they can all be two-dimensional or three-dimension. Okay, and this is example of a two-dimension. Okay? For the grid size, for example, if we want to have 6 blocks, right? Then if it's one dimension, you will just launch a kernel with a grid size of 6. But you can also launch the kernel with a two-dimensional grid size, like here, a 2 by 3 dimensional grid size. So in total, you still have 6 blocks. However, the blocks index will be referred as block index dot x and dot y. Okay, if it's three-dimensional, you will even dot z. Okay, so here's a two-dimensional example. So, for example, the first block, the block's index dot x will be 0 and dot y will be 0 as well. And for this block, it is actually indicated by the block index of dot x and dot y, and dot x will be 0 and dot y will be 1. Okay, so you can use a two-dimensional variable to describe the ID of a block. Same thing for the thread, so I won't repeat it again. Okay, and the way to declare the a two-dimensional or three-dimensional block size is the same as how you defined it for the grid. Okay? So for example here, right? The example we have here, if this is what we want to create, then you can see here when we launch the kernel, we will fit the grid size and the block size over here. And the grid size will be declared by dimension 3, and we assign it to a 3x2 dimension, right? And the block size is 5x3. So given this example, this is what we will see. Okay. All right. So why bother to have this multi-dimensional index? As we said, because of it's easy to programming, right? Our data is if our data is 2-dimensional or 3-dimensional in natural, then we should use 2-dimensional, 3-dimensional index to describe, right? To indicate, right, the coordinate or the index of those data elements. Okay, so it's a way to ease your programming effort. Okay, all right. So so as you can see that, right, you can declare your grid size in multiple dimension, and you can operate those threads on multi-dimension or linear array. So basically, you have to understand the definition and make sure when you calculate the index of the thread you want to access, you can translate in the right way. Okay. So for example, right, if in this example, if you run your kernel with just 1 block and 100 threads per block, then here the I should be equal to thread index, right? And on the other hand, if you use 100 block and 1 thread per block, then the correct answer here should be I equal to block index, right? And if you launch your kernel with a 2-dimensional, or you should just 1 dimension, but you have multiple block, then you need to use the block dimension, right, to linearize the address. Okay. And if it's even more complicated like this, it's a 2-dimensional block, then you have to even use the dot x and dot y. You can translate it in any way, but usually you want to make sure each thread handle a single element at the same time. You probably need to make sure you don't have any concurrent access on the data element. Otherwise, you may fall into those race condition problem, right? So you can depends on how you launch your kernel. You might need to adjust the index on your own. Okay. All right. So the next is the specifier we mentioned. Okay. So the specifier can be applied on the function or the variable, and they have different meaning to it. Okay. So if the specifier given before the function, that means whether this function will be compiled on the kernel, on the GPU, or on the CPU. So global, we already talked about it. It means the function is a kernel function, and only the kernel function can be called by the host and run on device. Okay. While the device function means the function, again, also it will be compiled into the GPU code, but also it can only be called from the device. So usually a device function is called from the global function, and the global function is called from the host function. Okay? And the host function, we usually don't use it because if you don't have any specifier or qualifier before it, like the code we saw before, then by default, it is the same as a host function. Okay? And finally, it's less often to happen, but you could do that by given host and device before the function. That means the code will be compiled in both CPU instruction and GPU instruction. Okay, it might make sense in some cases, might not make sense in other cases. It all depends on what's the code you written in the function. If it doesn't make sense, you will certainly receive some compilation error at the compile time. Okay? Okay. And then for the variable, okay, for the variable, again, there are a couple of more qualifier here, just a few, some common case we will need to use. But in general, the specifier or the qualifier before the variable indicate which memory well allocated for this variable. So device means the device memory, the global memory. Constant means the constant memory. Share means the shared memory. So that's right, easy to see. And there are actually, as I mentioned, GPU actually have other like texture memory or other memory space that you could use. Then you probably need to use different qualifier to specify that, so the compiler can know where to allocate that variable. Okay? Right. And finally, we will talk about a few API, and most of them you already saw, right? So in general, beside kernel launch API, we will use those memory operation API, including malloc, free, and copy. Okay. What you need to be very, very careful is that the malloc, because the pointer of the allocated memory is not returned by the return value of this function. So we have to use the pass by reference variable to get that result. And that result is a pointer address itself. So that's why you can see it's a pointer to pointer variable. Okay, so you need to be more careful on that in your programming. Okay, and also it's a device pointer because we have the host memory and we have the device memory. When we allocate the memory or when we do the memory operation, you have to be clear, right? You have to make sure you know whether the pointer is pointed to a device memory or a host memory. So here we use device pointer, means that this is a pointer allocated on the there's a allocated memory on the device. Okay. All right, and we need to know that because, for example, the memory copy can be used in both ways, from host to device or from device to host. We all use the same API here, and we use the kind to decide the direction. Okay, so in that case, as you can see over here, right, if it's a host to host, then both the source and destination should be a host memory pointer. While if it's a host to device, then the source should be a host pointer, right? Host memory address. And device should be a device memory pointer. So on and so forth. So you have to be careful, okay? So that's why when we name the variable, although we can name it in any way, but usually we will use some name that can easily tell whether that pointer is a pointer on the device memory or on the host memory. So you can avoid some programming error. Okay. Okay. So this is the CUDA main copy code. So this is how we can use it to move the data between the host and the device memory. Okay. All right. Finally, you should know is that the GPU compiler actually consists of two phases. Okay. Usually we say it's a two-stage compilation. And the reason for that is the hardware, the GPU hardware keep changing, right? every new generation comes up, it might have a different architecture and different instruction set. So the hardware change a lot and frequently. And the tool, right, like the compiler, the debugger, the profiler, those software, we usually don't want them to be changed or affected by the hardware architecture. We usually we will compile the CUDA code to an intermediate code called the PTX code. So it's like the Java bytecode. So it's a general, right, a unified code across all the computer architecture. And so all the software tool can be built around this PTX code without affected by the GPU architecture. However, when you actually need to run it on the GPU device, you need the target compiler to convert the code from PTX code to the hardware code, the GPU code. Okay. This two-stage compilation gives us more flexibility, right? Especially when we try to design some tool for programming and debugging, etc. Okay, so as in the lab, you will probably not see the PDX code. You only see the final bytecode. Okay, and the reason is just because that's the default setting for the compiler, for not to show you the PDX code because it's just an intermediate code. However, if you want to see it, you can easily generate that or keep that by giving some flag. So in the process, after you generate the PDX code, you will not remove it. Okay, and sometimes very useful because many tools they actually require the PTX code, not the bytecode, not the final bytecode. Okay. All right, so just have an idea. So in the future, if you saw some of the tool that require the PTX code, you will know what's going on. Okay, and of course, the first level, right? In the first stage, the compilation, besides generate the PTX code, you will also code the C compiler, right, to compile the CPU code. Okay, so you will generate the code for both CPU and GPU depending on the function, the specifier of your function, right? All right, so that's it for the CUDA API, and that's actually enough, right, for us to start look at some real CUDA code. We will do that on Thursday. We'll go through a few example code to make sure you know how the CUDA code is written, so you can at least complete the task assignment from the lab, because it also required you to modify some code. Okay, so do some porting already. Okay. All right, so that's it for today's lecture.